GaP, a graph as policy multi-agent self-learning harness for variational automation, VA tasks.
You know what's fascinating? Robots can now handle tasks that change day to day without constant human oversight.
Exactly. Most robot learning research focuses on super general systems, but commercial automation needs reliability and safety. Variational automation is about robots doing variable tasks like picking up different shaped items or pouring coffee with varying amounts.
Interesting. So how does this actually work? I mean, they can't just guess what to do every time.
So instead of one giant instruction list, you've got mini experts working together.
Pretty much. An orchestration agent splits the job into chunks and assigns them to skill agents like getting a camera frame or planning a move, then executing it.
Got it. But how do they make sure these agents don't get confused or try to cheat?
That's where the harness comes in. Think of it as structured environment limiting what each agent can see and do at once. So no single agent has total control.
Ah, like safety rails for code generation. What's new compared to older systems?
It builds on robot task planning and ROS, but adds multi-agent learning so they improve together without tripping over each other's outputs.
Okay, so it sounds like a smart combo of organization, safety checks, and teamwork. What's next for these systems?
The authors created 8 new benchmarks, some sim-based kitchen tasks, others in real-world industrial settings with robots actually doing the work.
So we're looking at robots handling unpredictable jobs while staying safe and effective. All right, Jaimyn, let's dive into this graph as policy.
Sure thing. Think of GaP as a chef taking natural language instructions and turning them into step-by-step cooking plans.
So those are just high-level ideas, right? How do they actually get turned into something the robot can do?
Exactly. Those ideas break down into semantic parts via MORSL, Modular Open Robot Skill Library, a cookbook with predefined skills, so instead of inventing every move from scratch, you pick and choose proven techniques.
Got it. So we have language, skill libraries, then what?
Then comes the actual execution graph. The robot decides how to sequence those actions in real time. Nodes are individual tasks like move arm or grasp object.
Sounds straightforward enough. But what are the 3 detectors doing exactly?
Think of them as 3 different eyes looking at the same input. One is a broad detector that just says there's something here without being too picky about details.
Got it, like casting a wide net.
Exactly. Then comes the fun part, the VLM disambiguator. It watches what you've already spotted and decides which of those 3 is most likely correct when they all disagree.
So it's like having an expert who can double-check the others?
Pretty much. And then there's this segmentation step that separates each object from the background, almost like giving them their own little personal bubble.
That makes sense because you don't want one messy blob hiding all your targets.
Right. After that, they fuse depth information to build a 3-dimensional map, basically turning flat images into something with height and width.
So it's not just 2D pictures anymore?
Nope. You get this nice layered view where everything has its place in space. And finally, an oriented bounding box wraps around each object to show their orientation so you know which way they're facing too.
That's pretty cool because it tells you not just where something is, but how it's positioned.
Exactly. Now the outputs, they give you a name for each detected thing, an oriented bounding box to show its shape and direction, plus a mask that highlights exactly what part of the image belongs to which object.
And there's also this cloud of points, right?
Yes, that's the 3D reconstruction from depth data, giving you a sense of how tall or wide each thing really is in real space.
So if I'm trying to navigate around these objects, I have both their position and shape plus some kind of depth map?
You've got it. And all this happens fast. Single-shot detection means you don't need multiple passes over the data. It's quick, but works best in places where everything isn't crammed together too tightly.
So good for open areas with clear targets, but might slow down if things get messy?
Spot on. And that's why it's ideal for settings like warehouses or big halls rather than a crowded street scene.
Thanks for breaking this down. It's fascinating how all those steps come together.
So we just heard about this new perception module that's supposed to be a lightweight one-shot set of marks picker. What does that actually mean in plain terms?
Great question, Jaimyn. Think of it like this. Imagine you're handing the robot a quick sketch or label for an object. The system has 3 separate detectors, all looking at the same snapshot they get from the camera. Each detector tries to guess what's there and where it is. Okay, so 3 eyes but only one winner? How do they decide which one gets to be right?
Exactly. When the robot says none for its V-elem disambiguator, that means none of the detectors were confident enough. The system then cleanly picks what it thinks is the best guess and sticks with that.
This method really shines when scenes get crowded or lighting is less than ideal.
It's built for reliability over speed. Each shot gets one thorough check from all 3 detectors, so you end up with clean results without overlapping errors.
So if you're hunting for a specific item and the system confirms it's there, you'll see a clear-oriented bounding box, a crisp mask, and maybe even a point cloud for depth details.
And because it runs in a single shot, there's no error buildup over time. Each detection stands alone and accurate.
That makes it perfect when clarity matters more than raw speed. So this next part is about how the system figures out what's in front of it, right?
Imagine teaching a robot to recognize objects by their shapes and positions.
The process starts with an oriented bounding box around the main object, like drawing a tight 3D rectangle around it. Once that parent shape is located, the system narrows its focus, crops out distractions, and labels each named part inside with its own orientation. So you break down complex objects into meaningful pieces after finding the primary shape.
Exactly. And even small details like drawer pulls or mug rims get picked up because the system is tuned for well-defined small shapes within the cropped area.
That layered approach, big picture to fine detail, boosts accuracy in complicated scenes.
The outputs include an oriented bounding box, a pixel mask, and a point cloud of key points for depth understanding.
That spatial map becomes crucial when a robot later needs to manipulate those objects.
It effectively bridges vision and action by delivering both location and appearance information efficiently.
And there's more. This paper also covers tracking those objects over time in real-world environments. Think of it as a digital game where the robot follows an object using cameras instead of kids running around. What are the inputs for that tracking?
The system takes text prompts telling it what to find, then processes images on the fly to produce bounding boxes and point clouds in real time.
So it's all about reading in real time, making decisions based on what it sees, and wrapping up when conditions are met. That makes sense for handling objects in unpredictable environments.
Exactly. And that's why this approach is exciting. It balances flexibility with control, all driven by the robot's ongoing perception of its world.
All right, Jaimyn, let's dive into this bimanual crate lifting part. I've got to admit, watching robots lift things with 2 arms is kind of mesmerizing.
Exactly. The paper describes a scenario where both robotic arms work together in perfect sync to lift a crate using handlebars. It's like watching a well-rehearsed dance routine.
Oh, I can picture that 2 arms moving in lockstep, almost like they're holding hands while lifting. What's the deal with those waypoints being baked parameters?
Great observation. The inputs are essentially pre-programmed steps. The robot doesn't get to improvise here. Think of it as following a recipe instead of freestyling.
So, no improvisation? That sounds both reliable and restrictive. How does the system handle unexpected hiccups if everything is baked in?
Good question. While the core movements are fixed phase, the real-world execution still relies on sensors to ensure timing stays precise, kind of like a conductor keeping time even when musicians occasionally stumble.
That makes sense. And what about outputs? You mentioned something about done and world position results?
Right. Once they finish, the system confirms completion with a Boolean flag and delivers the final coordinates, basically saying the crate is safely lifted here.
So it's all about precision timing and flawless coordination between both arms. Fascinating stuff. But I wonder what happens if one arm lags behind?
That would throw off their phase lock, much like missing a beat in music. The system might need adaptive corrections, but that's not part of this particular setup.
So it's elegant but delicate. Thanks for breaking it down.
Exactly. Perfection is the goal, but reality always adds a little twist.
All right, Jaimyn, let's dive into this next part about grounding and the Indo-detect system. I'm still trying to wrap my head around how they're connecting text prompts to actual object detections.
Sure thing, Alex. Imagine you're giving a robot a simple instruction like pick up the red cup. The robot has to figure out what that means in real time using both its camera feed and any other sensors it's got. That's where grounding comes into play. It's all about linking those words from the prompt to something concrete in the scene.
Okay, so they're tying text to visual stuff, but how do they actually make that connection? I know they mention a neural network, but what does it look like in plain English?
Think of it like teaching someone to match flashcards. The robot has two main parts working together. One part is the actor, which decides where to move its arms based on the text prompt and camera input. It's essentially doing the heavy lifting in real time, even if it doesn't have all the details up front.
Got it. So that's the part actually moving things around. What about the other piece?
That would be the critic, which plays a bit like a coach. It evaluates whether what the actor did matches expectations based on sensory data, helping refine future actions.
Interesting. So it's not just blindly guessing, it learns from feedback as well?
Exactly. And they use something called an INNO detect network to process both visual information and text prompts. It outputs a confidence score for each detected object, which tells you how sure the system is about its guess.
Confidence scores. So if it's 0.8 on a box labeled cup, that means it's fairly confident?
Right? And they've got thresholds like setting them to 0.20 to filter out weak matches, keeping the results clean and relevant.
That makes sense. But what about all those inputs like image and text prompts? How do they feed into this network without turning it into a math equation nightmare?
Good question. They keep things straightforward by using standard data types. Images go through preprocessing to highlight edges, while text is tokenized into chunks. Then the network combines them in layers that learn patterns over time.
So it's basically translating words and visuals into numbers they can understand.
Exactly. And this approach lets them work with real-world scenes without needing tons of custom setups. Pretty clever for zero-shot detection, right?
Totally. Makes me wonder how robust it is when things get messy. But I guess that's what the testing phase will reveal. Any hints about its reliability?
They mention evaluating performance using metrics like mean squared error between predicted and actual positions, basically checking if boxes line up with real objects.
That sounds solid. So they're not just guessing, they've got concrete ways to measure success. Any surprises along the way?
Well, one thing is how tightly text and visuals must align for high confidence scores. Even small mismatches can drop them out of the running.
Wow, it's like a dance between language and sight. Everyone has to be perfectly in sync. All right, Jamie, we're diving into this new part about open vocabulary object detection. What does that even mean in plain English?
Great question, Alex. Think of it like giving a robot the ability to understand objects based purely on text descriptions without needing to be trained specifically for each one. It's basically letting the system respond to any object just by reading a phrase.
So instead of teaching it only about cats, dogs, and chairs, we're asking it to recognize anything from a bicycle to a medieval castle on its own?
Exactly. The inputs are an image, a list of text queries or prompts, and some thresholds for confidence.
Interesting. What's the difference between P and prompt here, and why do they use two different letters for that same thing?
Good catch, Alex. The letter P is just a shorthand notation used in the paper to represent text prompts, while prompt is what we call them when writing out the description. They're referring to the exact phrases you give the system.
Got it? And those thresholds? Why 0.20 for both box and text?
Thresholds are all about balancing sensitivity and accuracy. A lower threshold means the system will report more potential objects, even if it's less sure, which is useful when you want to catch anything that might be relevant.
So a 0.20 box threshold means they accept detections with only 20% confidence?
Precisely. And the same goes for text prompts. They'll respond even if their certainty isn't super high, which keeps things open-ended.
That sounds powerful but also risky. What could go wrong if it's too eager to detect stuff?
Well, Alex, that's why thresholds exist. If they're too lenient, you might get lots of false positives or nonsense detections, which isn't what you want when trying to be precise.
Makes sense. So the core idea here is flexibility, letting a system react to any object described in text without prior training on that specific thing. That's pretty cool for real-world applications.
Absolutely. It could help robots understand new objects on the fly, though they'd still need good image data and robust prompts to avoid confusion.
So we've been talking about how robots can understand what's in front of them using text and images. But how exactly do they go from a list of words to actually finding objects?
Exactly. Alex, think of it like giving the robot a set of clues in the form of text queries and asking it to point out where those clues appear in an image.
Okay, so I'm picturing this like a treasure hunt. The robot gets a list of riddles or descriptions, like a red bicycle or a cat sitting on a mat, and then it has to find those things in the picture.
Right. Instead of just looking for one thing at a time, it can search for all the objects mentioned across the entire image simultaneously. It's like scanning a room with multiple flashlights at once.
Interesting. So what does this function actually take as input?
Well, you feed it an image, which is just the picture itself. Then there's a list of text queries. Those are your text inputs like a dog wearing sunglasses.
Got it? And those thresholds? Why 0.20 for both box and text?
Thresholds are all about balancing sensitivity and accuracy. A lower threshold means the system will report more potential objects, even if it...
I've been hearing about this new VLM backend that can answer questions based on images and text.
Exactly. And one of the key features they highlight is a function called VLM query.
Okay, I'm intrigued. What's the basic idea behind it?
Think of it as asking the model to look at an image and then respond with either a yes or no based on what it sees.
Interesting. So how does the model actually know what to look for in the image?
Well, the input is twofold. You've got a text prompt that sets the context and an optional image that provides visual information. Together they form a query. The model then processes both modalities to decide if the answer is affirmative or not.
I see. So it's like a hybrid reasoning task where vision and language converge.
Precisely. It's designed for scenarios where you need quick, factual verification from visual data, like confirming whether an object in picture matches a given description.
And what would the output look like?
The model spits out a Boolean, either true or false, and sometimes an explanation. This makes it more transparent than just giving a binary answer.
That sounds useful for applications where accountability matters, such as medical imaging or safety inspections.
Exactly. Now the paper mentions that they call this function VLM query. The inputs are straightforward. First, there's a text prompt. Second, optionally an image is provided. The output is just a Boolean answer, yes or no, and sometimes an explanation.
So it's not some complex chain of reasoning, right?
Not at all. It keeps the pipeline lean by focusing on direct classification based on multimodal input. That's part of why they emphasize configurability. They want you to tailor how much visual detail matters versus textual context depending on your use case.
I like that approach because it avoids overcompalchicking things up front.
Exactly. Simplicity can still yield strong performance when the model understands how to weigh both inputs correctly.
And what about reliability? Can we trust those yes-no answers blindly?
The authors stress evaluation on standard benchmarks, but they also note that confidence levels vary depending on input clarity and prompt quality. So it's not infallible. It works best when the image is well resolved and the question is specific enough.
That makes sense. It's like asking a smart assistant to confirm something you already suspect. It helps validate your intuition rather than replace it entirely.
Spot on. Think of it as a second pair of eyes that either confirms or challenges what you think you know, provided you phrase the question well and give the model clear visual data.
So if I wanted to use this in practice, how would I structure my query?
You'd start with a concise prompt describing exactly what you're looking for, then attach any relevant image file. The system will handle the rest by comparing both modalities internally before outputting your answer.
And that's it? No extra configuration needed unless you want to tweak confidence thresholds or explanation modes?
Right. They keep the core interface simple, but allow advanced users to fine-tune how much weight the model gives each input stream if they need more control.
That flexibility sounds promising for real-world deployment where edge cases happen often.
Exactly. It's designed to be plug-and-play while still being adaptable enough for specialized tasks without heavy engineering overhead.
Okay, I think I'm starting to see how this could actually help people make faster decisions with visual data in front of them.
And that's the real goal, making multimodal reasoning accessible through a clean, focused API so developers can build applications without reinventing the wheel every time.
All right then, let's keep an eye on how they improve confidence calibration and error analysis over future updates.
Agreed. And remember, always double-check anything critical, because no model is perfect out of the box.
Imagine you're teaching a robot to grab something without bumping into anything nearby. The team focuses first on getting that single pick point perfect before worrying about the rest of the motion.
Exactly. They break the whole task into clear stages: approach, grasp, lift, and each stage gets its own detailed plan.
So instead of one big unpredictable swing, they handle it step by step, which makes debugging and improving much easier.
Right. That staged approach also helps keep performance steady across different situations because you solve the hard parts first.
And what do you actually get as output? Just a simple success or failure flag?
No. You receive full descriptions of every trajectory, joint positions over time, and clear flags if something went wrong so you know exactly where to fix it.
That's practical. It's like getting choreography notes after rehearsal so you can see which part missed the beat.
Exactly. Breaking tasks down this way is smart when reliability matters, especially with varied environments.
I'm sold. This staged method could really help robots grasp more consistently.
Thanks for breaking it down. Next, we'll explore how all of this works in real-world testing and what happens when plans hit unexpected obstacles.
So Jaimyn, why is focusing on a single TCP pose such a big deal?
Because in practice, robots often just need to secure one point first before worrying about the rest. It's a smart starting point for complex motions.
Makes sense. What are the inputs and outputs here?
You give them the target pose, an initial pose, world details like obstacles, plus optional settings such as approach distance.
So it's like setting coordinates to grab something specific.
Right. Then they return whether it worked along with full motion plans for each joint.
And if it fails, what does that tell you in real life?
It could be geometry issues or numerical problems, but knowing when and why helps avoid surprises during execution.
So they prioritize simplicity before tackling the whole system at once.
Precisely. They break down complexity into manageable steps.
Got it. Now about this function called plan to pose. It plans collision-aware paths to a specific end effector pose.
Think of it like mapping a car route that avoids traffic jams, except the car is a robot arm and traffic means other objects in its space.
What do you feed into plan to pose?
The target pose, initial pose, world configuration describing obstacles, plus optional offset for final position.
And how does it figure out the path?
It concentrates purely on geometry. No collision checks during generation, which makes planning fast, but means safety isn't guaranteed until later steps.
That sounds efficient yet risky. There must be a trade-off.
Exactly. Speed comes from ignoring collisions initially, so it's often used as an early step before adding safety layers.
So the output includes whether it succeeded or failed and full joint trajectories over time.
Right? It's part of the Kerbo toolkit under the name Plan to Pose. Plan for path planning to pose, because you target a specific joint position at the end effector.
Makes sense. If it fails, you know immediately if the goal was unreachable or calculation hit a snag.
And if successful, you get detailed motion plans, though extra checks are still needed before real-world execution.
I like how modular this is. It handles pure geometry well without getting bogged down by world data until necessary.
Exactly what makes these tools useful for quick prototyping and reliable planning in complicated environments.
All right, so we've got plan to pose. Then there's batch feasibility checking, checking many grasp candidates before committing to a path.
Think of it as screening potential grasps early on to avoid wasting effort on impossible ones.
So inputs include the environment setup and a list of grasp poses with their details, plus an approach offset for closeness management.
Right. The function returns feasibility flags for each candidate so you can skip doomed attempts immediately.
And what about corridor collision fraction?
That's a score indicating how likely the planned path will encounter obstacles while reaching the target, helping prioritize safer routes early.
Wow, it's like having a checklist before tackling something complex.
Absolutely. It all ties together so you don't waste time on options that won't work.
So if I'm thinking about this for real robots, does this save computation and frustration?
Exactly. Grounded in messy physical realities and imperfect sensors, it streamlines planning only when there's a genuine chance of success.
Sounds like one step closer to making batch grasping practical for everyday robots.
Right. It builds on feasibility checks first, so planning proceeds only if conditions look promising.
All right, Jamie, we've covered how robots plan moves, but what about ensuring those plans don't end in crashes?
That's where safety checking comes in, verifying planned paths are actually safe from collisions.
So they focus on confirming no obstacles block the way before execution. Picture a robot reaching up to grab something above.
Right. First, the system scans the object's 3D shape and spots where a grasp could work.
Then it filters those ideas by what the arm and gripper actually can do.
The planner checks each candidate for reachability and stability so the robot won't drop or miss when it tries.
What about things like orientation or height offsets?
An oriented bounding box tells where the object sits relative to the robot, and a z-offset sets how high above a reference point the robot aims. Getting that wrong can make the grab unstable.
So aligning coordinates correctly is everything before motion even starts.
Exactly. Even perfect plans fail if alignment isn't spot on.
That highlights just how vital spatial reasoning and careful planning are in robotics.
It's easy to miss the subtle math behind simple actions like reaching out and grabbing.
And that step, choosing a solid starting pose, is surprisingly complex, yet looks effortless once running. After selecting that pose, what happens next?
Detailed motion planning kicks in, moving the arm without bumping into obstacles or losing balance.
So picking a good initial position is really the first checkpoint in a longer chain of decisions.
Breaking big tasks into manageable pieces lets robots accomplish them step by step reliably.
And that modular thinking drives robotics forward. So they're trading speed for stability when things go wrong?
If it can't reach the pose within a set time, the system halts instead of looping endlessly, like resetting after 20 steps.
The numbers used like tolerances and step limits are tuned by researchers to match real conditions.
They balance precision requirements with allowable adjustments based on robot and environment.
At its core, it's about making sure robots move safely and reliably in the real world. Finally, when a robot follows a pre-planned joint trajectory, it's executing a series of positions and speeds set ahead of time.
Imagine a dancer who has memorized the entire choreography before stepping onto the stage.
Okay? But how does it know where to go? What's the input that drives this motion?
The inputs include a pose, desired position, and orientation in three-dimensional space, plus linear and angular velocities and a tolerance value to prevent drifting off course.
So this isn't just moving from point A to B in a straight line. It's more nuanced than that.
Right. The robot interpolates smoothly between points using Cartesian coordinates, thinking about positions as x, y, z rather than joint angles directly. This makes motion look natural and fluid.
And what happens if something goes wrong? Like, does it just stop or try again?
There's a timeout setting, 20 seconds in this case, to ensure the robot doesn't hang indefinitely. It's like having an emergency exit plan built into choreography.
I love how they're borrowing from animation and robotics together. Makes me wonder about real-world applications for something like this.
Imagine a robotic arm assembling delicate parts in a factory, moving through precise poses without jerking or overshooting. It's all about smoothness and reliability, two things that matter whether you're dancing or building cars.
All right. So we've been talking about high-level goals and strategies, but now let's get down into the nuts and bolts of how the robot actually moves its joints.
Exactly. This part dives into joint trajectory execution. Think of it like giving a dancer a choreographed routine instead of just telling them to move naturally. The robot gets a pre-planned path for each joint, like from Kurobo or Pyroki, and then we need to make sure it follows that path as closely as possible.
Okay, so the inputs are this trajectory they've planned out, and some settings like how much they're willing to bend the rules with tolerance. What happens next?
The robot takes each point in that pre-planned sequence, each joint's position over time, and nudges itself toward it using something similar to a PID controller, adjusting based on distance off.
So it's constantly checking and adjusting?
Exactly. Precision without overreacting. The tolerance parameter, like 0.01 radians, sets a buffer so tiny wobbles don't throw everything off. It's the difference between saying move slightly left versus demanding perfection down to the millimeter.
Got it. And what about those limits on steps? Why 120 maximum steps?
Max steps is a safety cap, so the robot doesn't try to leap too far in one go, which could cause mechanical stress or overshoot entirely. It's like telling someone not to sprint across a room, instead they walk smoothly and steadily.
So this whole thing is about turning an abstract plan into real-world motion while keeping things stable?
Precisely. The output isn't some fancy report, it's the actual commands that drive motors in each joint, and crucially, there's no direct feedback loop with sensors at every step. Instead, it relies on accurate predictions and smooth interpolation between points.
That makes sense. It sounds almost like choreography. Every move is scripted but still fluid.
Oh, definitely. But surprises happen when you actually run this in the real world.
Makes me appreciate how much goes into making robots move gracefully. So this is about turning plans into precise actions without losing that natural flow? We've been talking about moving robots along paths and then sending them back home.
Right. It's all about getting the robot to know where it is and return safely after exploring.
Think of a hiker finding their trailhead after wandering through the woods. This is what the paper calls move-to joints, telling joints exactly where to go.
Joint config lists each joint's target positions. Tolerance defines how close it needs to be, like aiming within a small circle around a target.
So if there's friction or an obstacle, the robot still knows when it's near enough?
Exactly. The tolerance sets a soft boundary. Once within that range, the joints are considered home, even if they slightly overshoot.
That makes sense. It handles real-world messiness while keeping precision in check.
It's teamwork over solo finesse. No extra inputs needed. Just tell it to go home when close enough.
Nice way to wrap up that part of the control system. Now, what about breaks between tasks? Think of a robot finding its favorite spot at home.
They use go to pose arm with instructions for arm movement and target pose in SE3 pose, a fancy term for position and orientation.
So it's like giving directions to settle into a comfy spot, no feedback required on success or failure.
Simple but powerful when environments are unpredictable.
We wipe all learned parameters and cached data before starting fresh, like beginning with a blank whiteboard.
Inputs are sensory feeds like camera frames. Outputs are action commands in digital space.
Resetting gives us reliable strategy testing without leftover effects from earlier runs. Now we dive into what happens during one simulation teep step. Jaimyn, what does SimBridge Step 1 actually do?
It resets everything. No lingering data, and sets up fresh initial conditions using a seed for repeatability.
Sensors and variables return to default states, like waking in a room with no prior context.
Step 1 runs one teep step of action, producing observation reward signal and flags for episode termination or early stop.
Think of it as taking a photo after each rehearsal to check progress before moving on.
Now consider Mayujuvteye Kunstavihing. It methodically guides the robot toward target joint positions without letting it go wild.
Like training a dancer learning steps one at a time, not all at once.
Targets include desired positions and tolerances, max steps cap effort if convergence stalls.
If things stall after 120 tries, that acts as safety net but could limit flexibility.
The reward function balances progress against waiting or erratic motion.
Outputs are observation, reward, and termination flags. Observation shows joint states, reward rates success, and flags indicate completion status.
Blocking ensures the robot respects proximity before calling itself done.
If it struggles, it stops gracefully with clear feedback instead of crashing.
And if conditions change mid-motion, the system pauses until safe continuation is possible.
Finally, per-object ground truth poses are detailed snapshots showing every joint's position, like recording each puppet string location in a show. So what about cameras? Are they just visual inputs for the robot?
Exactly. They act like eyes, giving each camera a view of the scene from different angles.
Got it. And then there are objects with known positions, like labeling toys in a box, so you can check later if anything moved.
Right. In simulation, we know exactly where every object should be, which lets us compare what the robot thinks versus reality.
So that means 3 main outputs: arm joint locations, camera images, and accurate object poses?
Yes, and this setup isn't just for simulations. It can transfer safely to real robots because everything lines up perfectly.
That makes sense. Why does accuracy matter so much?
Even a centimeter of error can derail a robot's plan when moving from simulation to reality, so precise ground truth is crucial.
Exactly. Precision makes the transfer possible.
And finishing tasks in simulation hinges on reliable completion cues. It's like balancing improvisation with structured strategy. Think improv meets chess.
Right? It's as if a tiny choreographer teaches itself daily.
Importantly, this isn't just theory. It actually works on real hardware and boosts adaptability and reliability.
That's all we have for today. Thanks for listening, everyone.
See you next time.